Problem number 9. So we're given a graph of a function. We want to horizontally stretch that graph by a factor of 2. And the hint is really helpful. All you have to do to accomplish that is double the x-coordinate of each point. For example, I'm looking at this first line. This point right here is the point 3, 3. To horizontally stretch it, double the x-coordinate. Well, that would turn it into 6, 3. Nothing happens to the y value. Okay, how about this point? This is 1, 1. Well, that will change to 2, 1. How about one up here? 4, 4. That's going to change to 8, 4. That's a little bit off the grid. 0, 0. Well, if you double 0, you still get 0. And I think I have enough points now that I can connect the dots. It's still going to be a line. It's just been a little bit stretched out. Maybe one on this side, on the negative side, would be helpful. Let's see, -3, -3. That's going to move to -6, -3 when I double that value. And so if I connect those new dots, I basically end up with this picture. Here is the graph horizontally stretched out. Let's take a look at this V-shaped graph. Just a similar idea. Let's find a nice spot here. Here's one. 2, 4 is now at 4, 4, doubling that x value. And let's see, 3, 6 would now be at 6, 6. 0, 0 is not going to change. And let's see, on the other side we've got -2, 4. That's going to end up being at -4, 4. We've got -3, 6, I believe. -3, 6. Yes, that's going to go to -6, 6. And that's plenty. I'm still going to have a V-shaped graph. It's just been stretched out a bit to the left and to the right. Problem number 10 has a follow-up question. What's the only point that did not move when we drew those new graphs? And of course, in both cases, that was the point 0, 0. 0, anything would not change in the case of a horizontal stretch, because when you double 0, nothing changes. So horizontal stretches are always from the y-axis and then outward to the left or to the right. Problem number 11, I'm looking for the simplest negative coterminal angle. These are all in radians, and we know that you can find coterminal angles by simply adding or subtracting multiples of 2 pi. So I just need to subtract enough 2 pi's until I get down in the negative area. Let's see, in this first example, I'll have to get a common denominator of 4. So that would be 7 pi over 4 minus 8 pi over 4. And that becomes negative pi over 4. Well, there's a negative angle. I'm done. Let's see, 11 pi over 6. If I want to subtract 2 pi, I'll just go ahead and get the common denominator. That would be 12 pi over 6. I'm just rewriting 2 pi so that it has a denominator of 6. And that's going to give me negative pi over 6 when I subtract. The next one, let's see, I'll rewrite 2 pi as 4 pi over 2. 3 pi over 2 minus 4 pi over 2 is negative pi over 2. And then the last one, let's see, I'll rewrite 2 pi as 6 pi over 3. And when I subtract that, it looks like I get negative pi over 3. I suppose I could have also done this problem with pictures. For example, 7 pi over 4, we know that angle. It's the fourth quadrant angle with a reference angle of 45 degrees. So obviously, if I wanted a simple negative angle that would get there, it would be negative 45 degrees. In other words, negative pi over 4. I could have used that strategy on all of these problems as well. In problem number 12, I've got this equation sine x equals 3. And I'm being asked, what is the solution of this equation? In other words, what x value could you plug in there that would make it true? Obviously, I'd be looking for an angle since the sine function takes in angles. How am I supposed to answer this? Well, maybe I could think real quickly about the unit circle. After all, no matter what angle you put in on the unit circle, you always get the b coordinate out. The highest b coordinate you could ever get would be up here. This is the highest spot on the unit circle. There is no b coordinate higher than 1, which means this is an impossible equation. There is no solution to this equation. You can't have a sine value of 3. If I wanted to try to verify this on the calculator, I would have to go to the inverse sine function. The inverse sine function takes ratios in and sends angles out. Let's see what happens. So in the calculator, I would type sine inverse of 3. And notice what happens. I get an error. The calculator is saying you can't do that. There's no way to work that out. So that verifies what we were thinking. Letter C says we could have thought about the graph of the sine function. Think about our hill and valley graph that we have. There is no value on this graph that's higher than 1. 3 is up here somewhere, and the graph just does not hit that number. The maximum y value on the graph is 1. Or letter D, we could look at the unit circle, which we already did. The maximum b coordinate, as we said, is 1. There is no sine ratio bigger than 1. And then number 13, we want to quickly review drawing the basic cosine graph from negative 2 pi to 2 pi. So I know that the main initial period runs between 0 and 2 pi, so I think I'll do that first. I do want scale at all the usual spots, so I'll mark that on there. Obviously, I'm going to need the 1 and the negative 1. Cosine is the vase, so that's high, middle, low, middle, high. And I'll connect the dots. If I want to go over to the other side, though, I'm just going to need to make those evenly spaced tick marks. I'm counting by pi over 2s. It would be the same over here on the left. So this would be negative pi over 2, negative pi, etc. All those same values, just negative, all the way out to negative 2 pi. And the pattern is just going to repeat the other direction. So here would be another middle spot. Here's a low, and then a middle, and then a high. And then it's just a matter of connecting the dots, so it looks like that nice curvy cosine shape. This turns out to be 2 full periods of this function, and we've got all the scale marked at the high, middle, and low spots of the graph.